Okay, so we were proving some facts about finite sets. Let me grab this. And we proved the pigeonhole principle. Now we're going to prove that if you take a subset of a finite set, it's also finite. Now, I think I'm going to spend this lecture with theorems about finite sets, which might be boring for you because, as I said, because we have a good understanding of the notion of finite, these are all like, the statements at least, they're intuitively obvious. They require some work if you try to prove them formally. The reason I'm doing this is to show you the proofs, like, yes, any subset of a finite set is finite. That's obvious because if the whole thing is finite, if you can just enumerate the whole thing by natural numbers, if you pick any subset, you should be able to do the same. But why can you do that? Like, I want you to basically learn how you prove things about natural numbers. One way is induction. And in order to prove the pigeonhole principle, we kind of used an induction argument. I mean, we actually used an induction argument, but not with the proof of the pigeonhole principle itself, but within the proof of the lemma that we used for pigeonhole principle. Now I'm just going to prove that any subset of a finite set is finite. And we are going to use induction again, okay? Because this is basically a statement about natural numbers. Not at surface, but it really is a statement about natural numbers. Okay? So we proceed by induction. Let I be the set of all natural numbers such that we have the following. Every subset of X is finite. This is why I said it's actually a statement about natural numbers. What I want to prove is the following. What this really says is, for every natural number n, if a set X is bijective with n, if there's a bijection between X and n, then every subset of X is equinumerous with some other natural number. So this statement, at its core, it's a statement about natural numbers. So we again prove it by induction, okay? Now what I do is, and this is as I said why I'm doing the proofs, like the statement is intuitively true, right? Any subset of a finite set is finite. But how do you prove this? You prove this by induction. The point of me doing all this work is to make sure that you understand how to do induction. Maybe I should just summarize it like this. Anyway, we're going to do induction. We form the following set. I take the set of all natural numbers such that the following property of sets holds. For every set X, if X is equinumerous with n, then every subset of X is finite. Basically, I'm collecting all natural numbers n such that this statement is true for sets of that size, okay? Now, we wish to prove that I is all of n. Because in that case, what I will have proven would be the following. Any subset of a finite set. A set is finite if it's equinumerous with some natural number. So if you can show that this is true for all n, then that would show that given any finite set, every subset of that set is finite itself, okay? So we want to prove that I is n. The claim is, 0 is in I clearly since Well, the only subset of the empty set is the empty set. If you plug in 0 here, you're claiming that for all x, if x is equinumerous with the empty set, then every subset of x is finite. Well, the only set which is equinumerous with the empty set is the empty set itself. And the only subset of the empty set is the empty set, which is finite. So the claim holds for n equals 0. Now, assume that some natural number n is in I, okay? We wish to show that the successor of n is in I. So what do we want to show? We want to show that this statement for all x blah blah happens is true for successor of n. So let x be a set with cardinality successor of n. When I say cardinality, I mean the following. This is equinumerous with this set, okay? Now, this is what I used for, this is the notation I use for equinumerous sets. If A is equinumerous to B, then I write absolute value of A equals absolute value of B. But when I have a natural number on one of the sides, I'm just going to drop this absolute value just as a notational convention, okay? So when I write this, this means that there's a bijection from x to S of n, or the other way around, which are equivalent. Okay. So let's say that I have a bijection from S of n to x. We want to show that every subset of x is finite. So for every y subset of x, y is finite. Okay? So let y be a subset of x. Again, we're going to split into cases. If this y is a subset of the image of n under f, then y is finite by as f of n is cardinality n and n is an I. Now let's say that we're in this lucky case. Maybe I should draw a picture. I take a subset y, 0, 1, 2, and I have a bijection from S of n to x. This is supposed to be a bijection. I didn't write that down. Okay, this is a bijection. Say f is a bijection. So I look at the image of n. So I ignore this guy. I just look at everything above it. This is the set n. I look at the image of this. If y is contained in the image of this guy, then I'm lucky. Why? This set is finite. It has n elements by the following bijection, okay? This is the bijection from n to this set, okay? So this set has n elements, it's a finite set, and by induction assumption, every subset of this is finite. In particular, y is finite because it's a subset of this. So this is a lucky case. Now, let's say that we are not that lucky. This is not a subset of the image of n under f. Then f of n has to be in Y. You look at the image of this guy, if it's not containing Y, this image, Y has to contain f of n. Because if it did not contain f of n, then Y would be automatically a subset of the image of this, okay? That's simply by the definition of the image, okay? And so Y minus, now this is an element of Y, so let me take that element out. Now, this guy is contained in the image of n under f, okay? So what I did is the following. Let me redraw the picture. In the second case, I look at the image of this guy. The image of this guy does not contain Y. The only way that this can happen is f of n is contained in Y. Now I take this f of n out. Now the remaining thing has to be contained in this, okay? And now I'm going to use the induction assumption. Since n is an I, and again, I simply observe that this is a finite set with n elements, we have, okay, sorry for this, we have that this set is finite. Okay, I have to name this guy. Let's name this guy. No, I don't need to name it. I'm going to go the other way around. There exists a bijection H from some natural number to this set, okay? I'm not going to name it. So this is a subset of this set. This is finite. It has n elements because n is inside I. By induction assumption, any subset of this set is finite. What does finite mean? It means that there is a natural number m such that there is a bijection from this guy to this guy. This is simply by definition of finite. Then, now I'm going to take this guy, H, and I'm just going to add one more pair to that. You see, this maps natural numbers less than m to these guys. I'm going to add this pair. I'm going to map m to f of n. Now, this is a bijection from, I expanded the domain to successor of m. This is the set of all numbers from 0 to m minus 1. I also include m, so I get the set of all numbers from 0 to m included. That's the set S of n. Now, this is a bijection. I'm taking that bijection and I'm adding this guy. So what do I do to the range? I just expand the range. I just extend the range by one element. I'm just adding f of n. Well, if you add f of n to this, it's a bijection apparently to the set Y. So Y is finite in this case. Okay? Now, what have we proven? Y is finite, thus every subset of X is finite. And that finishes the proof. Why? And so, maybe I should add one more line. And so, S of n is an I. I assume that n is in this set. I took successor of n. I want to prove that this is inside. In order to do that, I picked some x. with successor of n many elements, and I wanted to show that every subset of that set is finite. At this point, I did that. That part of the proof finishes over here, and then it follows that this argument is true for every x. You see, let x be that. The argument that starts from here to here, it shows that for every x with successor of n many elements, this is true, so this claim is true, therefore this is true for all x. So successor of n is in I. And that finishes the proof, okay? So subset of a finite set is finite. Questions about this? No? Now, where's my purple chalk? Okay, it's over here. How many minutes do I have? I have 28 minutes, so I can do both of these lemmas. Now let me do the following. Let me prove the following. If you have two finite sets, their union is finite. Yes? Yes. It's this notation, f of x, x in n. It's the usual function notation. You apply f to elements of n, and you form this set. Okay? It's the range of n under f. Okay, so let's prove that the union of two finite sets is finite. Let's pick two finite sets. Let x and y be finite sets. What does finite mean? It means that, say, I have two bijections from m and n to x and y respectively. Okay. The function h from m plus n to x union y given by, now I'm going to define a function as follows. The value of this function at I is f of I if I is between 0 and m. 0 included, m not included. So basically what I'm doing is, this is m, this is n, this is x, this is y. Okay, maybe they intersect, maybe they don't, I don't know that. So I have this bijection f, 0, 1, 2, dot, 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 it goes up to m minus 1, and I have this bijection g from 0, 1, 2, dot, 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 m minus 1. I define the following function. It's from m plus n to the union. For 0, 1, 2, dot, 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 up to m, my function behaves identically like f. And for the other guys, if my I is between m and m plus n, it's supposed to be I minus m. G of I minus m, okay? Now, you may object, we haven't defined minus. Okay, we haven't defined what this means when these are natural numbers. How do I define subtraction? Well, if you want, I can do it. I can explicitly write this out as this is supposed to be g of j, where j satisfies the following. j plus m equals I and so on. I don't want to do that, so you know what this means. So I'm not going to define subtraction like that and leave it like this. Now, then the function blah blah given by that rule is a surjection from m plus n to the union. Why? Why is this a surjection? How can you prove that this is a surjection? Take any element in this union. That element either belongs to x or y. If it's an x, then look at the inverse image of that element under f. Say that element is, I don't know, 5. Then h of 5 gives you that element. So you can map to any element in here using f. Okay, let's say that you take the element you took in the union, it belongs to y. Look at the inverse image of that. Let's say you got 7. Then what you do is you look at h of m plus 7. Then that guy will automatically map to that element. So it's easy to show that this is a surjection, okay, using the fact that these are bijections. I keep forgetting writing bijections, okay? These are bijections, both of these functions. So using the fact that these are bijections, you can easily show that this is a surjection. Now look at construct the following function. Yes? Yes, because there's a typo in the notes. You see, in the notes, I changed the places of this, but according to that, this is supposed to be n in the notes, which I'm going to fix later. Yes, what I'm saying is it's wrong in the notes. In the notes, it should be I minus n. This is what it's supposed to be. Otherwise, it's not going to make sense. Anyway, this is a surjection. Now, for each element in the union, let wz be the least element of H inverse of the set, okay? Then the map, let me write down the definition of the map, then I'm going to explain what this is. F from the union to the sum given by f of z goes to w sub z, it is a bijection. Well, no, I'm going in the other direction, it's an injection. So now construct the following function. Okay, we have a surjection from this set to the union. What I do is, now I create an injection in the other direction. For each element, I look at the inverse image of this. And I send this guy to the inverse image. The problem is, if you take an element in the intersection, the inverse image of this might consist of two guys, because maybe one element from here maps to that, maybe some other element from here maps to that. So there might be two guys in here which map to the same guy in the intersection. So what I do is I map this guy to the least element that I can find here. Because natural numbers are well ordered, I can always find I can just say that I'm going to choose the least element which maps onto this. Okay? And when you do that, you can get an injection from this union to m plus n. Okay? Now, m plus m is finite because it's a natural number. This set, the range of this guy is finite by the previous lemma. Subset of a finite set is finite. And so, this x union y is finite, because if there's an injection between, if there's a bijection between you and some finite set, then you're also finite. As f from x union y to its image is a bijection. Okay. So, union of finite sets are unions of finite sets are finite. Now let's prove that this is the last fact I'm going to prove about finite sets. Let's prove that the power set of a finite set is finite. And you may have realized that that proof was surprising because we did not use induction for that. For every other proof, we kept using induction. For that one, we did not need that. Anyway, we want to now prove that if x is finite, then the power set of x is finite. Again, this is intuitively obvious. Why? Actually, this is intuitively less obvious than the previous ones, but still obvious. If you have a finite set, you want to construct, like you want to take all subsets of that and put it in a single set. You want to say that that's also finite. Now, how are you going to choose subsets? For each element, you're going to put it either inside the subset or not. So what you can do is, if you have, let's say, 7 elements, you can just throw a coin 7 times. If the coin comes heads, then you're going to take the element. If it comes tails, then you're not going to put the element inside the subset. And for every head and tail sequence that you can construct, you can form a subset. Conversely, you can argue that for every subset, I have a head and tail sequence which corresponds to that. And then, I mean, you can try to prove it like this, but then you have to prove that the set of all head and tail sequences of length, in this special case 7, is finite. Okay? So it's not going to make the proof any less difficult. I mean, it's intuitively obvious that there are like finitely many choices because like heads and tails, you have 2 choices. You're throwing the coin 7 times. You have like 128 elements. You're going to try to argue it like that. That's fine. But if I ask you to prove it from our axioms, we define what it means for a set to be finite. We define power set. Now prove this. How are you going to do that? We're going to use, guess what? Induction. Again, because this is essentially a statement about natural numbers. That informal proof I was just talking about, like try to actually count things, saying that if this has n elements, this has 2 to the power n elements. If you try to prove that, you will again have to use induction. Like this is why I said it doesn't make the proof of this lemma any less difficult, because I mean, you're taught these in the discrete mathematics course, right? Like if you have 2 choices for every box, if you have 7 boxes, then you can make like 2 to the power 7 choices, like 2, 2, 2, 2, 2, yes. That's an informal way of counting it. If I ask you to actually prove that that's the case, like how many functions are there from this set to this set? How many possible functions are there? This many. If I ask you to prove this, you will have to use induction again. You cannot simply say that I have n many 2's, therefore the number is 2 to the n. Yes, but what the hell does that mean? Dot, dot, dot. In order to prove something like this formally, you will have to use induction. So we're basically going to do the exact same thing, but we're going to do it, we're going to write it in a different way. Basically, all the informal arguments I was talking about and the argument I'm going to write down, they boil down to the same thing, some induction argument, okay? So we proceed by induction. on, I don't need to tell you what I'm going to do induction on. We proceed by induction. Let I be the set of all natural numbers such that for all sets with that size, the claim is true. This is finite. Okay? I collect all natural numbers n such that this claim is true for sets of that size. By the way, I didn't write this on board, but if some set X is equinumerous with some natural number n, then I'm going to say this has n elements. Anyway, clearly, 0 is inside the set I, since, well, there's only one set which is equinumerous with 0, namely the NP set, and the power set of empty set has one element, so this is finite. There's a bijection from this set to 1, namely the identity bijection in this specific case. So this claim is clearly true for 0. Assume that it is true for some n. Now, we want to show that it's true for successor of n. We wish to show successor of n is an I. So how do you show something like this? You need to prove a universal statement. For all x, blah, blah happens. How do you prove something like that? You take an x and show that that blah, blah part is true. So let x be a set such that the premise of this implication holds, such that with successor of n many elements, okay? Say f is a bijection from successor of n to x. So I'm just going to write here bijection to denote that this is a bijection, okay? Note that now let me write down the claim, then we're going to understand why this is true. Okay, I chose some set x. This has size successor of n, so there's a bijection from successor of n to x, okay? What I do is the following. Okay, successor of n is the set of all natural numbers 0, 1, 2, dot, dot, dot. It goes like this up to n. It includes n. Now what I'm going to do is I'm going to look at the image of n under f. So I'm just going to apply f to these guys and look at their image. Their image, the image of the set under f, the range, it's going to miss one element because it misses one element there. Now I have a claim. Let's understand that claim. The claim says the following. If you pick a subset of x, that subset either is a subset of this purple region. If you get a subset of x, that subset is either a subset of this purple region, or that guy is obtained as follows. It is the union of some subset of the purple region, union. It's of the form some subset of the purple region union f of n, okay? And this is clear. Why? Pick any subset of X. Now, this subset, it has some intersection with this guy. Okay? F square bracket n. The stuff that's possibly not in the intersection can consist of at least one element, because this purple region misses only one element. So this is the actual picture, okay? This is my subset, this is the part. So it can only miss one element. Then you can write down, if it misses an element at all, then you can write down this subset as, maybe it doesn't include all of this purple region, maybe it also leaves some element in here. It doesn't matter. If it misses some element, it misses at most one element, namely this guy. The point f of n. Then you can write down this subset as a union of, as the following union. Some subset of this purple region plus this guy. Some subset of purple region plus this guy. So if the white subset, if the subset you choose, if the element you take from here, it contains f of n, then it's of this form, so it's in here. If it does not contain this guy, then it's already contained in the purple region. So it's already an element of this. So, and the other direction is clearly true because these are all subsets of X, okay? So we have this equality. Now, both sets on the right-hand side are finite by the induction, since n is an I. Now, this is a set with n elements, okay? By induction assumption, since n is an I, the power set of this guy is finite. There's an obvious bijection with this set and this set. Namely, send y from power set of this set to y union the singleton containing f of n. Okay, send y to this guy. So there's an obvious bijection between this set and this set. Because this is finite and there's a bijection between this set and this set, this is also finite. So both sets are finite. This is finite follows from the fact that n is an I. This is finite follows from the fact that you can easily construct a bijection between these two. By lemma, the union of two finite sets are finite. And so, power set of successor of power set of X is finite, okay? Therefore, now for any X with successor of n many elements, we show that the power set is finite. Therefore, successor of n is an I. And so, I is inductive and hence all of natural numbers. Thus, maybe I should just write this last line. For all n, for all x with, for all n and for all x, if x is an element, then power set of x is finite. So we proved that I is all of n, which means exactly the following. All natural numbers n belong to that set. Thus, for all n, for all x, if x is n elements, then its power set is finite. This simply says every finite set has a power set which is finite. Okay. Now, that's that. Exercise. Using induction, show that this is true. Okay? So if X has an element, then its power set has 2 to the n many elements. By the way, this is okay. For any finite set X. I'm going to write finite set here because we haven't learned about it. Infinite, well, we talked about infinite sets, but we didn't really learn what it means to write, like what this means for an infinite set. When we learn about infinite sets, you'll see that this is simply true for all sets. Whether X is finite or infinite, it doesn't matter. This is simply true. But then, in order to make sense of that, I have to talk about cardinality of a set and cardinal numbers and cardinal exponentiation and so on. That's going to come later. So prove this using induction. Now, that's that. I have 3 minutes. Let me talk about what we're going to do. So let's recap all we did today. We defined what it means for a set to be finite. A set is finite if it's equinumerous with a natural number. A set is infinite if it is not finite. Now, being infinite has some equivalent characterizations. You probably learned infinite as follows. A set is infinite if there's an injection which is not a surjection on that set. That's an equivalent definition, but that's really called being Dedekind infinite. Next lecture, we're going to show that being Dedekind infinite is the same as being infinite. So forget about infinite sets for now. We define what it means for a set to be finite. If a set is not finite, then it's called infinite. And we proved basic facts about finite sets, such as if 2 sets are finite, their union is finite. If a set is finite, its power set is finite, and so on. We proved that for any natural number n, any injection from that natural number to itself has to be a surjection, and as a corollary, we proved what's known as the pigeonhole principle. If you have an m element set and if you have an n element set, if m is greater than n, then any function from this m element set to the n element set has to be a non-injection. Okay, I just invented some terminology. Non-injection means that it's not an injection, so it can't be one-to-one, okay? So we proved that basically using induction. So that's that. Next lecture, we're going to talk about infinite sets. More specifically, we're going to talk about countable infinite sets. We're going to prove various basic theorems about countable infinite sets. You see, all these were intuitively obvious, like, you know, 2 finite sets is finite and so on. When it comes to infinite sets, the human intuition usually fails, okay? So the theorems and lemmas I'm going to prove about infinite sets, they're not as obvious as these ones. They're going to be more non-trivial. They're going to be of more non-trivial nature. And that's that. What do I want to say now? Yeah, I think I'm going to stop, but before that, let's just again be amazed at what you can prove with induction, okay? So induction is important. You see, all these are proven by induction at the core. So learn how to do induction well, okay? Because if any point in your life in future you need to prove something about natural numbers, well, you're going to probably use some other theorems. So you're not going to really use induction, but when you actually look at the proofs of those theorems that you use, you will see that at its core, everything proven about natural numbers, they're basically proven by induction, okay? Induction is important. And when we talk about ordinals, I'm going to rephrase this and I'm going to say transfinite induction is important. So, I'll see you on Tuesday and have a nice weekend.